Okay, so now we're heading into the motion capture chapter, right? Which is kind of fun. This is something that everyone kind of remembers or recognizes from, you've seen a million, well, maybe not a million, but you've seen lots of like DVD behind the scenes things of people getting motion captured. This kind of really, I think, came into the public consciousness with Gollum from Lord of the Rings, was when people really started to sit up and take notice of motion capture, although motion capture had been used for a long time before that for a lot of different reasons. So one of the first, memories I have of motion capture for movies was from Titanic, where basically they motion captured a lot of people just kind of like walking around, and then they used them to animate characters in long shots of the ship on the deck. A lot of the characters that you see walking around on the ship of the Titanic are from mocap, right? And you're far enough away from them that you don't really notice them that much. And people have been using motion capture for a long time in a lot of non-video or non-visual effects contexts, right? So one thing that is apparently common is to do motion capture for like orthopedics and for sports. So like they will put mocap markers on an athlete to decide, whether there's something that they can improve about their swing or about their gait or something like that. They'll put it on you for recovery from some sort of surgery to tell whether your gait is kind of like back to normal. There's a lot of kind of specific motion capture stuff for, there's, apparently a lot of hand motion capture for, kind of orthopedics specifically related to the hand. And of course, there's lots of motion capture these days in video game studios, right? So pretty much any sports game, right, is composed of tons of strings of mocap to make the activities of the players on the field look really accurate, right? So there's lots of stuff to say about how do you take the motion capture data and translate it into how a 3D animated character works. And so, because this course is focusing on computer vision largely, I'm going to kind of stop just short of saying how do you take the raw mocap markers and drive an animated character with them, because there's lots of stuff that has to happen between the raw marker trajectories and the animation. And so kind of where I'm going to stop is how do you take the mocap markers and basically get this articulated moving skeleton, right? That's kind of like the starting point for everything that comes next. And as we'll talk about a little bit later, there is a lot of work for animators to take that type of motion capture data and make an animated character look lifelike and realistic. It's not like there's just this turnkey solution where you take the mocap, you press a button, and suddenly the character looks great. A lot of times the mocap data is not even really used directly to drive the character. Sometimes it's more like used as reference for the animator to understand, I can see how a person would move, now I can see how I can tune my animation rig to move similarly. You would be, if you watch a lot of behind the scenes DVD stuff, you would get the impression that the mocap data is somehow automatically transferred. But in fact, there is a ton of human effort and a ton of expert artistry involved with making those animated characters come to life. And so we'll talk a little bit about that kind of towards the end of the mocap section. Okay, so, all right. I guess I didn't open this up. So here's what you all came to see, the picture of me in the motion capture suit. There's a better picture coming. So basically, this is the fundamental idea, right? You are a performer who is in this kind of, embarrassingly skin-tight bodysuit, and there are markers that are attached to your joints, basically. And so the idea is that you take the performer, and as we'll talk about in more detail, that the positions of these markers are mapped into this kind of 3D skeleton, and the skeleton only knows where at this point we only know where those marker positions were in 3D. So for example, I've got this headband of 4 markers, and you can see that headband of 4 markers here. But then what we really care about is turning this set of external markers into a skeleton, an articulated skeleton that has bones and joints that map onto what a human has. So you want to turn the surface markers into something that says, okay, where was the 3D position of my shoulder? Where was the 3D position of my elbow? Where was the 3D position of my wrist? And then the idea is that you use these markers to drive a animated character, which hopefully moves in a similar way to the original mocap. But again, it doesn't need to be like this kind of slavishly accurate, one-to-one mapping. And so what we're going to talk about in this chapter is kind of, today we're going to talk mostly about how do we go from the raw video to this kind of 3D positions of the markers. And then next week, we'll talk about how do we go from the marker positions to the positions of the skeleton, which is really the problem that we care about. We'll also talk about how do we take these motion capture kind of sequences, because usually, you know, a mocap stage is not necessarily a very large place, right? So if you want to capture, you know, a long take of a character, you know, running across a big field, you're probably going to have to stitch multiple takes of mocap data together into one thing that looks kind of seamless. And so we'll talk about this kind of motion editing. And then on the last day, we'll kind of talk about, you know, are there ways around this problem where you don't have to wear the goofy-looking suit? You know, could I do this in my normal street clothes and get reasonable motion capture? And there's been a lot of computer vision research in doing exactly that. It's not quite as accurate as you know, markered mocap, but you know, for a academic research perspective, you can do pretty well these days with street clothes. So let me just say that we're going to focus on the kind of world of mocap where, you know, again, you're in the skin-tight bodysuit with the markers. There are a bunch of alternatives, some old and some new. So one of the first ideas for mocap was this magnetic motion capture. And so the idea was that, you know, as we'll talk about, one of the issues with markered motion capture is that, you know, if I have a marker on the back, on my back, for example, it's not going to be visible from all the cameras that are kind of looking at me from the front, right? So I have some dropouts of different markers. Whereas if you have a magnetic sensor that basically responds to a magnetic field in a room, from that purpose, you know, your body is kind of like transparent to the magnetic field. And so a magnetic motion capture system, in theory, you know, every marker is always visible, but the problem is that, you know, it's a bulky system. You can see this woman has all these cords and stuff attached to her, and you can see there's this trunk of, you know, wires leading off of her leg, right? So I think that there do exist kind of battery-powered or wireless magnetic motion capture systems now, but this is not the norm by any means these days, because, you know, one reason is that magnetic motion capture systems are very sensitive to big metal objects in the world. And so if you're on a sound stage or with lots of computers and equipment, then magnetic motion capture is going to get thrown off by all this other stuff. And so this is not really very common these days. Another option, and I apologize for the, you know, sexist models in all these pictures. This is apparently the marketing material. Another option that is can be precise, but also, as you can see, very cumbersome, is kind of almost like more of an exoskeleton, right? Where you have something that basically has rigid, you know, like rigid struts and movable joints attached to your body, and so that if I have something that's on my arm that can very accurately measure how my arm is bending, then I'm almost like doing a direct readout of what the joints are doing instead of, you know, trying to infer it from surface markers. But again, this is not, you know, as you can imagine, a very natural thing to be strapped into, right? And you rarely see this being used for visual effects. A third option is something that's kind of like more like the, you know, like for example, your Wii remote or your, I'm not sure whether the Xbox remote does it, but basically, you know, inertial and gyroscopic type of motion capture. Like your phone definitely knows kind of how you're accelerating. In theory, couldn't you strap like 20 iPhones to your body and kind of use the accelerometers? Well, you know, there are some inertial motion capture systems now that are kind of along those lines. Again, you have to kind of you can see that this person has like these kind of bulky, you know, sensor packets coming off of their body at different places, and that's kind of where they are in the person. So, and then they have these kind of, I'm not sure whether these are battery packs or what, or processors on their back. And then another possibility is, this is kind of like regular motion capture, except it's using bright red LEDs that also have a very high modulated blinking pattern, so you can tell apart which LED is which, right? So to the naked eye, it looks like someone wearing a bunch of little red lights, but the cameras are high-speed cameras that can detect, you know, this is blinking light number 1, this is blinking light number 2, based on their very high-speed blinking pattern. So, you know, there are lots of, you know, variations on the theme, but I think it's probably fair to say that the most common thing is to go into a studio like this, where this is actually the place we're going to be on Thursday, where you can see it's basically just like a big empty room, and what you have around the periphery of the room are these special cameras, and every camera looks kind of like this. And so the camera has a bunch of infrared LEDs around it and an infrared camera in the middle, okay? And so the idea is that these LEDs are pouring infrared light into the environment, and it's trying to pick up things that respond to infrared light. Okay, and so as you'll see, so basically we kind of learned already about the kind of fundamental theory of if I've got a bunch of feature points moving around the space, if I know where all the cameras are, then I can just triangulate in 3D where the corresponding points are, right? And so the first thing you have to do with a motion capture system is calibrate it, right? And this is just like the camera calibration problem we talked about from before. And so the way that you calibrate the system is with a wand or something that looks like this. And so here what you can see is basically just a stick with 3 balls on it. And here the manufacturer knows exactly how big the stick is, right? And so we know, for example, that the distance between this ball and this ball may be 10 centimeters, and between this ball and this ball may be 20 centimeters, right? And so what you do before you start the mocap session is you basically take this wand and you wave it around the space, and the tracks of these points give me the feature correspondences that I need to calibrate the cameras. And the calibration process is very much like what we talked about in the last chapter. And so this is kind of a picture of what the camera sees of the wand, right? And so you can see that, if you look back at this wand, there's kind of like two balls that are, kind of 1 unit from each other, and then these balls are like two units for each other. You can kind of see that I can figure out which is the left-hand ball, which is the right-hand ball by using the bright one in the middle to disambiguate which end is which, right? So basically, every feature point that I see is, or every time I see this 3-ball wand, I'm getting basically 3 XYZ coordinates. And as I wave this wand around, I'm generating lots and lots of 3D points for which I have, 2D projections. And so, and these, by the way, these bright dots here are the infrared lights of the motion capture cameras that are seen by this camera right here, right? And so, one thing to notice immediately is that, from the infrared perspective, you can hardly see me in this picture at all, right? I'm very dim. Even though this set of infrared cameras is really bathing the space in infrared light, it's not really as bright as a visual camera, right? However, the balls on the end of the stick are really bright. And so the reason for that is that these balls are engineered to be highly retroreflective, which kind of means like the way that your, the way that your bike tape or, something like that when you're biking, you have these retroreflective markers that you wear, or maybe like the back of your cat's eye, right, strongly reflects light back at you in the direction. So basically these balls are going to really bounce the infrared light strongly back in the direction of the camera, right? So that means that you really see these balls shining from the infrared point of view, and kind of conversely, you don't see much else other than these balls, okay? And so, again, luckily for the mocap operator, the calibration process is kind of hard-coded into the software that you buy. So before every session, you kind of wave the stick around, and then you calibrate all the cameras. So now you know where all the cameras are, and then you can triangulate points in 3D. I'll talk about that process in just a second. So then you got to marker up the person, okay? And so here again is the great picture of me in the mocap suit, and then you can see me from the infrared camera perspective, right? And so again, the mocap markers really stand out as bright, white dots in this world, and you can't really see much else about me at all, right? And so one thing about the, one thing is the marker placement, okay? And so, yeah, question?
Just a really quick question, going back to the calibration stuff, did
you
ever use the position of the lights from the other cameras to sort of position the cameras?
Yeah, that's an interesting question. Could you use the fact that you're seeing the other cameras as a calibration constraint? I guess that you could, but I doubt that they do.
Okay. I just thought it's something that I forgot to ask before. Sorry.
Yeah. I mean, I don't think that the calibration routines use those at all, will be my guess. But you're right that in some sense that would give you a pretty strong constraint on where the other cameras were, right? In theory, maybe you could do it without even actually seeing the stick, right? If you just saw where all the...
I think you need some sort of...
I think you need something in the middle of the space to do it, but yeah.
You could get a very good constraint on where that camera should be.
Right. Yeah, you kind of know where the camera centers should be from looking at these points. That's a good idea.
Anyway, sorry.
Anyway, that's okay. So, so again, this is what the person looks like. And so the first question is kind of how do you marker up the person in a way that is helpful, right? So one thing that's, really interesting about motion capture is that what you're doing is placing markers on the surface of the body and trying to figure out what's going on underneath the skin with the bones and so on. And that is biomechanically, not necessarily so easy to do, right? So you might think, okay, well, I'm just going to put a joint on, I'm going to put a marker on my elbow bone, right? And that's okay because I can kind of feel that bone, maybe through my skin pretty well. And so I know that my underlying elbow is not that far away from where I put the marker, right? But for something like on my shoulder, the shoulder is actually, so one thing is that you have to learn a little bit about biomechanics, and we'll talk about that in a second. But basically, what the body is doing underneath with the way that your bones are set up in terms of hinge joints and ball and socket joints and so on, you can only get at kind of coarsely by putting markers on the surface of your body, right? And so what you're trying to do is you're trying to place those markers to give you somewhat of the maximal information that you can get. And so, for example, they put a few markers basically where they can feel a bone, more or less. And so whoever gets markered up when we go to the mocap studio, you'll see that the technician is trying to place these markers in a way that they kind of feel around to find out, can I feel this bone here? And so there is this kind of like, biomechanical sub-knowledge that you could have in order to help you place these markers well. You shouldn't just be kind of slapping them everywhere. And so this is kind of like a picture of the configuration when I was markered up. You can see that, there are some markers that are kind of repeatable, like the elbow markers and the shoulder markers. This one here, like the one that's on my arm here, that's maybe more of a judgment call in terms of, all you have here is kind of like fleshy upper arm, right? There's no kind of, you could try and put it halfway, but it's not so easy to do. You've got a couple of markers, like kind of 2 points on the sternum, kind of markers around the pelvis. There's some markers on my feet, a couple markers down my spine. And then, there may also be some need to add some additional markers, like if you've got multiple people in the space at the same time, to kind of disambiguate person one from person two. So you may want to put like just an extra marker here, or extra marker here to say, okay, when I see this marker, I know it's person A, and when I see this marker, it's person B, right? Because when you've got multiple people moving around the space, you may get confused as to who is who. Yeah, and so, like I said, part of the reason that the mocap suit is embarrassingly tight is that you want to get those markers as close to the surface of the body as you can, right? Okay, so let's see. So that's kind of like the setup phase in the environment. Do you have anything to add? Did I miss anything interesting to say?
Well, kind of going off of the same configuration with multiple people, sometimes you also want to not have the markers be exactly symmetrical across one line.
Right.
So one thing, which I don't actually see in that picture, but we do a lot in the lab is on like the left leg, all the markers will be a hair lower than the right leg, so they will be really easy for the system to tell.
I see.
This is
I see. So some sort of left to right, or back to front kind of symmetry thing. Yeah, that's true. It looks like there's not really, it looks like these are pretty symmetric here. You would think that the front and back markers would be enough to disambiguate that. I was wondering, like, maybe there's like this marker here that's like kind of off-center on my spine. I was thinking that might be one of the things. Yeah. Because that's certainly not a, I don't think that's a biomechanical thing. I think that's just like they do their best, yeah. Yeah. So by the way, just one caveat for whoever gets dressed up. So I remember the mocap lab as being cold. So keep that in mind. I was cold when I did this. Plus I was barefoot. Will they let you do it with socks on?
I guess you could, but
They'd
there
have
would
to
probably
be
be a lot of motion when you're walking around with your socks.
Okay. All right.
and they'd have to be finger socks because it looks like you have some toe rings on.
Yeah, they well, it's not toe rings, but they have like this kind of just Scotch tape stuff onto you. Right? So just bear in mind that if you're going to be the one who gets suited up, you should have resistance to cold. Okay, so off of the embarrassing picture. Okay, so the first thing that you need to do when you see the markers, right, is to triangulate. So we can assume that we've solved the kind of calibration problem already, and so. What I would say here is basically marker triangulation. So on the one hand, you might think that all these markers really look the same, and it would be impossible to distinguish them as feature points. And you would probably be right. But then the other thing to think about is that once I've calibrated the cameras, I have like all this epipolar geometry too, right? So for example, if I see a bunch of markers out here, and I want to know, okay, so which one is which? Well, I see these points here, and I see these points here, and I see these points here. But if I think about the epipolar geometry after I've calibrated the cameras, if I think about, okay, here's one point in image 1, and I draw this line, and I think about, okay, so then where is the epipolar line in image 2? Well, that epipolar line in the corresponding images is generally not going to pass through multiple markers, right? Or if it does, there will be other cameras that I can kind of chain these epipolar lines to kind of disambiguate, which marker is which, right? So that's the whole advantage of having calibrated cameras, is that, when I think about shooting rays through corresponding markers, there's really only, if I've done it right, one point that is, reasonably close to all 3 rays that I would shoot out into the world, right? And so it doesn't turn out to be so hard to figure out which marker is which. The main thing that you have to do is think about, okay, so mathematically, how do I find this closest point? I guess that this is the picture that I drew here in a better form, right? This is the problem that we're faced with solving. And so kind of mathematically, the problem that I would pose would be something like this. So for every, for every camera, I have a camera center. And I also know kind of this direction that the camera is looking. And I want to find the point in 3D that is closest to all of these rays. And so in some sense, what I'd like to do is, if I kind of zoom in, I want to minimize the sum of square distances between the point that I discover and each of the corresponding rays, right? I want to make sure that those things are as small as possible. And so the minimization problem is something like, I want to minimize the difference between what I am trying to estimate and, for example, something like this, right? Where I'm trying to say, okay, find me the distances along each of these rays so that my, actually, maybe the way, yeah, so I think this is okay way to say it. This is a little bit clumsy, but kind of what I'm trying to say is, how far out do I go along each ray so that I can find a point that is minimally close to all the rays, right? And the book goes into the formula for how you solve this problem. It's actually like a nice closed form thing. If you know the camera centers and you know the directions of the cameras, then you can just kind of in one shot say, okay, so what is the closest point? Now, just as a comment, again, you may not necessarily see all the points in all the images, right? Especially because your body, right, is solid. So, for example, like I said, if there's a marker on my back, maybe only half of the mocap cameras are going to see that back marker versus the ones in front of me that don't, right? And so I'm not always triangulating with the same set of cameras every time. But the surprising thing is that the calibration of the system with this wand waving is so accurate that the markers are actually very precisely triangulated to within, I would say, millimeters, right? So the markers that you get generally look pretty good. And so ultimately what you have then is, you may still have some dropouts or some noise. And so, for example, what you end up with is in 3D, and I'll show you a little video of this in a second, you have kind of like this marker trajectory, right? So you can kind of imagine that you see this moving path of markers over time. And, in case where there's like a bad estimate or there's, no estimate, but you still have stuff on either side, then you can imagine that you could basically bring to bear all of the normal kind of like signal processing tools for interpolation, right? So if you could do some sort of outlier rejection and say, okay, well, I know that markers just can't move, more than a couple centimeters between frames, right? The other thing is that these mocap systems are generally fairly high-speed cameras. And so, one of the reasons for that is to capture, finer motion than 30 hertz, and the other reason is that, you don't have that much exposure time on the cameras, and so you basically are taking the quickest image that you can. And so you say, okay, well, if I've missed this marker, then I could just use, for example, a spline or even like a quadratic or something like that to connect the dots, basically, and fill in that, I'm going to fill in this marker that I actually got a poor estimate of or never saw. Or you could also use that to help out with, okay, suppose that I had like a long string of dropouts because of occlusion or something like that. Then you could say, okay, well, I'm going to kind of connect through here, and then I'm going to use my hypothesis about the sampling rate to fill in these trajectories and kind of break, kind of put this back together into one like unbroken trajectory, right? So, these are some things that are probably going on under the hood of the software that processes the markers. I mean, sometimes you may have to go in manually and touch this stuff up yourself, and then I think that probably when you hit the process button in the software console, it's doing a bunch of this stuff on its own, right? Because what you usually get at the end is something that's already looking pretty good. Although I have seen the grad students in the lab kind of tweaking markers when they find out that after the automatic process, you have to go back to it. So we'll probably see some of that tomorrow, is exactly how much tweaking comes off of the system after you've processed it. Another thing that you can do, by the way, is here you're kind of, like I said, you could bring all of the machinery of like generic signal interpolation and so on to bear on this kind of problem. But then you could also exploit the fact that that these markers are coming from a human body. And so you can imagine that if you collected lots of examples of where these markers were for natural human motion, that you would know that there were correlations between markers, right? So for example, suppose that I have my, suppose this is my guy, right, with his tiny head, right? So this is a little bit better. So shoulder, elbow, wrist, right? So suppose that, for some period of time, for whatever reason, I lost this elbow marker, right? But I had the shoulder and the wrist marker. And so here's a case where, again, I should be able to exploit the fact that the elbow is correlated to the shoulder and the wrist to fill in what the elbow could be doing as missing data, right? And so that's kind of like a machine learning problem where you imagine that what I do is I have training data where what I would have would be basically like the XYZ of marker 1, the XYZ of marker 2, and so on, all the way up to however many markers. I mean, there may be like, up to 40 or 50 markers, at least you probably have 30 markers on the person. And so basically what I have here is like a kind of a 150 by 1 vector. I gather a whole bunch of these vectors together, and then I can kind of learn the correlations between these vectors, the natural relationships between the vectors. And so probably before I do any sort of analysis, I want to bring them all into some sort of a coordinate frame where, it doesn't do me any good if they aren't aligned. So let's imagine that I always align them in such a way that my kind of, I'll show you a picture in just a second. There's usually like a kind of a root, they call it. So basically, let's see if I can draw this right away. So if I draw this guy here. So there's usually a kind of a root marker that is kind of like right around here, where if you align this to the same 3D position and orientation, then you can kind of get everyone in the same forward-facing orientation. And so the idea is that now that I have a bunch of these training data samples, what I could do is I could say, now I learn the underlying relationships between the markers, which is probably much lower than 150 dimensional, right? So there's only so many ways that my body can move, right? I can't have my, I can't have my elbow like below my hip joint very naturally, right? That's an uncommon motion. And so what I should be able to do is abstract out, instead of thinking about this as a 150 dimensional vector, I should be able to reduce the dimensionality to, only a few inherent dimensions, maybe, I don't know what, say 20 dimensions, just as a guideline, right? And then you can use that using an example, using the algorithm like principal component analysis to say, okay, now suppose that I missed, this whole chunk of video, but I saw these markers and these markers. I can then interpolate what are the most likely, missing data points given my model for, how the human body is actually likely to take configurations, right? So that's a little bit more complicated, and that requires you to actually collect a bunch of training data, but it can be done. I mean, it's also probably underlyingly much more sophisticated than this, so maybe I wouldn't necessarily train on the whole body. So for example, there's probably no underlying correlation between like how my right leg can move and how my left arm can move, right? So knowing this stuff doesn't help me at all with this stuff. Whereas probably the left arm is really highly correlated with, my torso, right? So maybe what you have is a set of models for different kind of body regions where you say, okay, if I'm trying to interpolate my elbow, then I really need to know about the wrist and the shoulder and the left-hand side of my body. Whereas if I'm trying to interpolate my knee, then I need to know about my pelvis and my, my hips and my feet, right? So you basically build like multiple models for different parts of the body. I don't think that these days there is usually a lot of noise, like kind of noise in the electrical engineering sense of like high frequency stuff that comes off of the markers. If you have that, you'd probably just like, I would be surprised if that happens. That's probably some sort of problem in the system. And the other thing is that, again, as a signal processing person, you might think, well, I can just kind of smooth out the noise, right? And so I can make these smoother marker trajectories. But in practice, the high frequency stuff is often the really nuanced and interesting stuff that you want to capture with the mocap system, right? I mean, if all you wanted was like the kind of low frequency stuff of somebody walking, well, you could generate that with a gate program, right? And it would look okay. What you want to do, I mean, the whole point of capturing motion capture data is to get this kind of human subtle motion that is hard for an animator to guess at, right? The whole point is that you want to get this kind of really naturalistic motion, right? And so that stuff is usually high frequency, little ticks of your body, that kind of stuff. If you smooth it out too much, you'll lose it, right? And then you have something that's not very useful. Another thing that's kind of important, especially for things like sports, is a lot of stuff is very high frequency naturally, like punches and kicks, and if you don't want to smooth that stuff out, you want to get the impact of the blow, and so that again is something where you don't want to do too much smoothing. So this may be a good point. Let me just show you some mocap data. So this is a program called Mocha with 2 Ks, and I can show you some stuff that came out of my let's see here, my mocap session. Let's see. It's a little bigger.
Quick question.
Yeah.
The standard pose that a lot of these mocap systems have you do at the beginning is like cactus side, and so
right.
As you do it, I can see it kind of doing
yes.
a little bit there.
I'll play this while you're talking. Yeah.
Yeah. So basically, why the side?
So I think that the reason for this is basically the motion capture system wants to associate different semantic things like head, chest, mid, back, so on. And so they ask you to kind of exercise all of the, all the limbs kind of one by one. So like, when I turn my head but everything else is stationary, they know that's my head marker, right? And when I do this, they're figuring out where the arms are, and then I do, here you're probably figuring out where are the wrists, right? And where is the pelvis. And so actually it's pretty interesting. So as you can see, right, even just from these, whatever it is, 30 moving dots, right, it's very easy for a person to pick out that this is, number one, this is a person and not just like 30 random dots. But also, I mean, the motion seems human, right, because it is human. It's not like animated motion that has been, automatically generated, right? You can see there are these little wiggles, and like here I can't balance on my foot very well, so like there's, that kind of thing would be very difficult to animate, and that's one of the reasons people like mocap data, is that it gives you this kind of nuance, right? And so then once they've calibrated you, so here's like kind of just natural motion. Hold on a second. Trying to figure out how I select all the markers. There we go. Right. So here basically I'm just like, you know, clowning around.
Great acting.
Yeah, you like that?
Did you do any theater?
But here you can see, actually, that was probably, there was a point where I was scratching my head, right? And you can see that, the wrist markers are, fairly far away from, here, like that, right? Scratching your head, right? The markers that you see on the hand, right, are actually physically far away from the actual surface of the head, right? So it's not like you get exactly what you want. So there was a study, actually, way back when. Here's another one. I think this is one where I'm, like, catching a ball or something and throwing it back, or like the sports video kind of thing. So here I'm kind of waiting for the ball, and then I catch it, throw it back. Yeah, so it's very easy to tell like what's going on, right? And so actually there was a kind of psychology experiment from many years ago. I think it was maybe in the 40s or 50s, where a person basically attached like light bulbs to just a few joints on a person, not even like a full-on mocap markered situation, but just like maybe one on the elbow, one on the knee, and so on, and then just ask people to look at the video of the lights moving, and people could immediately tell this is a human. You could probably even tell gender, man versus woman. You could tell what they're doing. You can tell what their pose is, and so in some sense that's a testament to the human visual system, right? Is that with very little information, it's very easy for you to automatically tell, hey, this is a person, right? As opposed to, two independent people or a set of randomly moving lights. I mean, it's like not even a question that you can identify these as a person, right? So, so actually reading those original psychological studies is kind of interesting. So anyway, this is the kind of data that you get off of the system, the raw markers, right? And so the next thing we need to do is turn those markers into a skeleton, right? The underlying skeleton. And so there's two kinds of related ideas, right? One is called forward kinematics, and one is called inverse kinematics, right? So forward kinematics is basically saying, okay, so if I knew the skeleton and then I kind of posed the skeleton, where would those motion capture markers be on the body, right? So in some sense, that's what you don't know, right? So if I knew where the skeleton was, it's pretty easy to figure out where the surface markers should be. What I want to do is the inverse kinematics, where I know the surface markers, and now I want to find the most likely skeleton position. So we're going to talk about that next week. But what I want to talk about now, just for the moment, is just like how do you parameterize the skeleton part? How do you do forward kinematics? And so for those of you that are knowledgeable about like robotics, for example, this kind of thing comes up very frequently in robotics. Like inverse kinematics, forward kinematics is like, really what things are all about. So for example, there are important problems like, for example, if I want a robot to reach out and grab something, right? So I know what I want to grab, and I want to find, for example, the path that the robot takes there. That's kind of like an inverse kinematics problem to figure out, I know what the goal is, I know what the desired thing is, but I need to figure out how does the underlying skeleton need to move to get there, right? I know the forward kinematics of the robot. I can know how to move the robot to get to a certain place, but that doesn't tell me how to learn the path, right? So path planning and stuff like that. There's a lot of relationships between this stuff I'm talking about today and what you might learn in a course like Robotics 1 or Robotics 2, or if you were doing robotics research. So, for example, if you ever have a chance to go over to the CATS lab on the 8th floor of the CII, you can see our robot lab that has these basically dual-armed, humanoid-looking robots that, they have different length, they have different, joint, they have basically the same joints as a human, but they have very different limb lengths, right? So you've got these very, like, long-armed robots, much longer arms than humans. And it's a big problem of how do you teach these robots to do stuff, right? You can do the forward kinematics where you can direct them to a certain point, but what you really want them to do is to learn how to move around and pick up stuff automatically, and that's much more of an inverse problem. Okay, so the human body, right? So I don't know much about biology, but I can give you my basic idea. So basically, there are different kinds of joints in the body, right? So the fundamental two different kinds are the ball and socket joint, like your shoulder, which you can rotate, shoulder like clicking around as it is. So which you can rotate in kind of like, a spherical angle. And there's something like your wrist, which is really more of a 1D, like a hinge joint, right? And so what you can do is you can kind of say for every important joint in the body, is it more like a ball and socket joint, or is it more like a hinge joint, right? And so, for example, your shoulder can rotate around, your neck can rotate around, your hip joint can rotate around, but then other things like your knee and your elbow and so on are really more like hinge joints. And this is an extreme simplification, right? Because actually, for example, your wrist, can, you can move all these joints a little bit, you can move all the hinge joints a little bit outside of just like this one dimension of freedom, right? And actually, even the shoulder joint is not just like literally, like you put the two Legos together and you rotate around, right? I mean, there's like a lot of complicated muscles that make up the shoulder. I think the shoulder actually has like 3 joints that are kind of working together under your skin to move your shoulder around. And so this is an extreme kind of anatomical simplification of what the body is doing. So again, for those people that know a lot about biomechanics, it's kind of interesting to think about what is the right way to parameterize this. But for mocap purposes, this is probably the level that you would stay at. And so here what you have are basically, a series of spherical joints in gray, hinge joints in white, and then this big guy in the middle in the pelvis is what they call the root. And so that's basically the thing that you use to align different, poses of the same person or different people. You need to have something that you say, okay, this is the kind of center of the coordinate system of the body, right? So kind of everything kind of flows out from the root. And so if I want to know, for example, how, so this is important for forward kinematics. You say, okay, first I tell you what is the 3D position and orientation of this center point. And then I can propagate, I can propagate a series of angles to tell me where other joints are. So for example, if I want to know where is my elbow, what I do is, okay, well first I tell you your spine is hinged by 20 degrees and your neck has got these 2 angles and your shoulder's got these 2 angles and your elbow has this angle. So basically you kind of build out from the root a set of angles that tell you where that final position is, right? And these black points here are basically things that don't hinge, they don't rotate at all. These are called, in robotics world, you call them end effectors. Basically, they're like the, so for example, I've got my wrist, and at the end of my wrist, forget about my fingers, suppose I just have like a flappy, palm. So at the end of this is the thing that I can actually use to push on the world with, right? So for a robot, it's very important to know where are the end effectors that I might use to, pick up a box or something like that, right? And so for every joint has some corresponding kind of limbs, and the limbs have certain lengths. And so, again, part of the calibration process for motion capture is also, I think, estimating what those limb lengths are. And I think that's what happens. So, I mean, when you do the calibration process, especially the one where you're kind of exercising all the joints, my guess is that it is estimating, okay, for this, for person A, their upper arm length is X and their forearm length is Y, and the assumption is those things don't change over time, I think, once you've built the skeleton. And so, of course, in the real world, I mean, of course, your bones are not like very compressible, but in the real world, that may not be like super true, or at least you may want to leave a little bit of slot for the fact that the knowledge of the joints is not like super precise. And so you may want to say, okay, I am going to fit the skeleton to the mocap markers the best I can, subject to the constraint that the limbs are, bone length, estimated from calibration plus or minus, X centimeters to give me the best fit, or something like that. But I mean, realistically, I don't think you see the bone lengths changing that much. Okay, and so, like I said, I don't want to do, let's see what I got here. Yeah, so here's an example of kind of like how forward kinematics would work. So it's like saying, okay, so if I want to figure out where is my wrist given the shoulder as the frame of reference, the first thing I do is I would tell you, okay, so what are the 2 angles of the shoulder? What is the length of my forearm or my upper arm? That gets me to where the elbow joint is. Then I tell you what is the hinge of my elbow, and what is the length of my forearm, and that gets me to where the wrist joint is. And so basically, I build out from some center a series of angles and known limb lengths to figure out where is the object that I care about, right? And so mathematically, what I would say, mathematically the way you do this is you say something like, okay, so I have, if I want to find my wrist position, what I would do is first I would rotate my shoulder, and I would know how long my shoulder is, or my upper arm is. And then I would rotate my elbow, and I know how long my forearm is. And so basically, this would give me some point in the 3D space. And so, for example, if I suppose that both of these rotation matrices were the identity, that's like saying no rotation in my shoulder, no rotation in my elbow, like this, for example, then that might be saying, okay, well, if there's no rotation there, then the position of my wrist is just the sum of the lengths of my forearm and my upper arm, right? That gets me to this point on the x-axis. Whereas if my shoulder is the identity and my, and my elbow is bent like this, well, then I have, something that goes out this way and a rotation and something that goes out this way. So I have a point that's out here in kind of x comma y space, right? And in general, that could be like anywhere. So I can basically trace out anywhere I want, okay? And so actually, this kind of raises, while I'm talking about the elbow and the shoulder, this kind of raises one of the, ambiguities about inverse kinematics. We'll talk about this more next week. Basically, the idea being that, if I tell you the shoulder and the elbow angles, then it's easy to find the place in 3D where that is, right? But if I tell you where the wrist is, there is kind of this ambiguity about where the shoulder and the shoulder and the elbow could be, right? So, for example, this is because I'm getting old, I can't rotate so well. But so basically, there's this kind of like 1 degree of freedom in how my shoulder can rotate, keeping my elbow fixed, that results in the same position of my wrist, right? And so the inverse kinematics problem is kind of like saying, okay, so what is the most likely configuration of my body to bring those markers into those positions, right? There is this, so if I didn't have the elbow marker, there would be this substantial 1 degree of freedom ambiguity, and I have to choose the one that is somehow most physically accurate. Man, my bones are like really clicking when I do all these things, because I need to exercise apparently. Okay, and so if you want to make this more complicated, again, if I go back to my picture of this guy, right? So again, in theory, to get to any point on the body, I have to push my way from the root through each of these joints out to the position that I care about, right? And so you can think about that as basically the composition of a whole bunch of kind of rotation and position matrices. And so maybe it's better to use something like this. So kind of what I'm getting at here is that for every joint, this is kind of like weird notation, just bear with me. So kind of what I'm getting at here is that to get the position of some end effector, what I usually have to do is I have to propagate the known position of the root through a bunch of rotations and translations, right? The rotations tell me the angles of the joints, and the, these 3x1 matrices here basically encode the lengths of the limbs that connect the joints up. And so what I'm doing is I'm kind of connecting up, a bunch of bones and joints to get me to the final position, right? And so one thing that comes up a lot in motion capture then is kind of parameterizing all of these rotations and stuff. And so one very common way to parameterize rotations, especially for motion capture, is using what are called Quaternions. And so if any of you have ever done like 3D computer graphics, you may have come against Quaternions already. And so, just as a quick aside, so, rotations basically, when you first learned about rotations in, I don't know what, multivariate calculus, for example, you probably see things like, you've got like some theta, phi, I don't know what the other angle would be, psi, right? These would be like Euler angles that would tell you, kind kind of like pitch, yaw, and roll, right? If you've heard of that from a more aeronautical world, right? So that's the way that you would specify angles when you first learn about them. But then you kind of realize that that's not really the best way to do things. And so one of the reasons that you don't like to do things that way is something that's called Gimbal Lock, which is kind of something that I don't really have a great handle on. But basically the idea is that there are certain kind of critical configurations of these angles that once you get into one of them, you can't kind of, you're maybe you have a pound.
Yeah, so it happens when, for example, your X and Y axes kind of line up with each other, and then it's really hard to get them to move apart again.
Yeah,
Right.
I think you lose it.
You lose a degree of freedom.
On
Yeah.
YouTube, one good example, and on Wikipedia. But if you're manipulating a camera in a game, for example, and you look
Right.
straight down at the ground,
Right.
you might run into a problem where you can't recover your camera anymore.
Right,
because
right.
of the gimbal lock.
Yeah, that's right. So you lose this degree of freedom, you can't get it back, right? So Euler angles suffer from this kind of problem. One thing that we talked about briefly, I didn't hit it too much in the last chapter, but there's also what you call axis angle parameterization, and that's pretty good in general. That basically says that, okay, so I tell you a vector, and then I tell you basically, you know, the rotation around that vector. And so basically the vector in 2D is kind of like, you know, there's like a spherical angle here. Usually I represent this as a unit vector plus an angle, right? So there are three numbers here, but they're parameterized in a slightly different way than Euler angles, right? And then if I know this vector, then a quaternion is basically a different way of using the same information. Quaternion. And so a quaternion is basically saying, okay, if I know these angles, then here's a different way of writing that as a 4 vector. Right? So I still have only 3 parameters, but I'm writing it as a 4-dimensional vector. This turns out to be useful because it's easier to figure out how to do things like, for example, interpolating between different rotation matrices using quaternions as opposed to trying to use Euler angles or something like that. So there's a homework problem I assigned about, you know, how do you try to convert between different representations of Euler angles and other possibilities. Another thing that you can use is, you know, there's also a lot of rigid motions in this kind of thing, because basically you can imagine that what I'm doing is I'm changing a coordinate system from, you know, one position to some other position where there's a different orientation. And there's a rotation matrix and a translation vector that characterizes this rigid motion. It turns out that you can represent this rigid motion using something that's called a twist. And so a twist is basically like this, where this is my, you know, kind of before position, this is my after position, and it turns out that instead of thinking about a rotation matrix that, you know, translates from here to here, I can think about this as finding a vector in 3D where I rotate a certain distance around the vector and then I move along the vector. And so that means that there are, you know, there's a vector I have to figure out, there's a center point I have to figure out, there's an angle I have to figure out, and there's a distance I have to figure out. So I can take the same 6 parameters and represent them like this kind of, you know, twist where I rotate around this vector and move along the same vector. And these twists are also useful in terms of, if I go back to this picture, right? So these matrices here, where I kind of where I'm composing things with the forward kinematics, it turns out that it's easy to represent these things in terms of these so-called twist parameters. So again, the details of that are a little bit hairy, and so I'm going to leave that for reading offline. Okay, and so I think where I want to end up today, basically, is that at the end of the day, what we have is a kinematic model, right? The kinematic model is made up of, you know, this picture that looks like the guy with the skeleton, and then to fully specify where the skeleton is, all I need to do is I need to tell you the bone lengths and the angles that represent the joints, and the angles are usually represented as quaternions or twists for kind of making my computations easier. And as I said, usually you can count up, and I think it's actually one of the homework problems I assigned is to figure out, okay, so how many degrees of freedom does this crude kinematic model have? And then you think about, okay, so then I think about how many markers are on the body for mocap. Maybe I have like 30 to 50 markers, each of which is a 3D position. And then what I have is this kind of inverse problem where it's over-constrained, saying, okay, I've got all these visible markers that I come from my motion capture system. How do I estimate the positions and orientations of all these underlying points, right? And so that's kind of like the inverse problem. We'll talk about that next time. Okay, so let me pause and ask any questions about just like the setup of how of the basic. This is more like terminology of motion capture, right? This is kind of just getting us started. Okay. So what we're going to see when we go to the motion capture studio is to make these concepts a little bit more concrete, right? You'll see someone hopefully dressed up in the suit. You can watch the real-time skeleton moving around, or at least you can watch the real-time markers moving around. Do you see the real-time skeleton too? I don't think so.
Well, yeah, it depends. I'm not sure if they'll have
Right.
time to go through the entire process
Okay.
for everyone, but if they demo something at the beginning, you'll be able to see like kind
Right.
of what they should do out there.
Yeah, because usually what I remember is that they collect the data online, and you can maybe see a crude thing, and then there's a processing step that basically does the inverse kinematics to give you the skeleton, then you can watch the skeleton dancing around, right? Okay, so that's going to be Thursday, and then we'll return to the technical part on Monday. So let me just shut this down here.